In section 3.2, we look at polynomial functions and their graph. So first we start with a definition of a polynomial function. And this can be a little bit overwhelming at first, but basically a polynomial function has the form f of x equals a sub n times x to the n power plus a sub n minus 1 x to the n minus 1 power plus etc. all the way down to the constant term. So these a sub n's and a sub n minus 1's, etc., those are just coefficients. N is the power, which is the degree of the polynomial. And so you can see that the way we have it written here, we have the highest power of x first, and then the next highest power all the way down. And the domain of a polynomial function is the set of all real numbers. So in our first example, we just want to identify which of the following here are polynomial functions. So we start with the first one here, g of x is equal to 3 plus 5x. First of all, I can rewrite this as 5x plus 3. And this is essentially 5x to the 1 plus 3, and you can think of 3 as being 3 times x to the 0, because x to the 0 equals 1. So you can always put this sort of imaginary power of x here to help you kind of understand what you have. So what we have here is a leading coefficient of positive 5. Our highest power of x is x to the first power. And then we only have one more term after that, which is our constant term, and that's just positive 3. So yes, this is a polynomial function because it fits the format of what we have up above. In the second example, we have h of s is equal to 2s times s squared minus 1. Notice that I can distribute here, and we can rewrite this as 2s to the third power minus 2s. And this is also a polynomial function. You can see that we have a leading coefficient of positive 2. The degree of this polynomial is a third degree polynomial. And it has a couple of terms. Also, the variable is s instead of x. That's not a big deal. You can change the variable. And so yes, this fits the definition above for a polynomial function. In the third part, we have f of x is equal to the square root of x squared plus 1. So even though x squared plus 1 would be a polynomial, the fact that you have a square root around the variable makes this not a polynomial. So this does not fit the form of what we have up above. So, in summary, yes, this is a polynomial function. Yes, this is a polynomial function. And no, this one here is not a polynomial function. Now let's talk about some properties of the most basic type of polynomial function, which is often called the power function, and that is f of x is equal to x to the n power. And we break this down into two cases. On the left side here, you'll see that we're talking about x to the n power where n is an odd positive integer. And on the right-hand side, you'll see that we're looking at n is an even positive integer. So when n is an odd positive integer, this case here, the domain of the function is all real numbers. The range of the function is also all real numbers. And then we have this thing that we call end behavior, which I'll talk about here in just a second. Now what I've done for the purposes of understanding this is I brought in the graph of f of x equals x to the first power, f of x equals x to the third power, and f of x equals x to the fifth power. These are all examples of odd powers of x. And I want you to see that the domain of this function is all real numbers. It's pretty easy to see that. And the range is also all real numbers because the function goes forever up and also forever down, covering all the values on the y-axis. And this is true for all three of these functions. So we can see why the domain is all real numbers and the range is all real numbers. Now, in terms of the end behavior, when you have an odd power of a polynomial function like this, the end behavior is that as x goes to infinity, x to the n goes to infinity. So what we're talking about here is if you zoom in on the x-axis a little bit, as x gets larger, so this is what happens when x goes to infinity, you can see that the function itself is also going to infinity, right? Because as x gets big here, the function values are also getting big. That's what we mean when we say as x goes to infinity, x to the n goes to infinity. Now, notice in the other direction, as x goes to negative infinity, you can see as x gets large in the negative direction, the function values are also getting large and also in the negative direction. So we can say that these function values are going to negative infinity. This is what we call the end behavior of the polynomial. In other words, we don't really care so much about what happens in the middle, but as x gets big, the function also gets big. And as x becomes a large negative number, the function also becomes a large negative number. And notice this happens for all three of these graphs here. For the first power of x, the third power of x, and the fifth power of x. And we can generalize that this happens for all odd powers of x. So again, as x gets large here, the function values here are getting large. And as x gets large in the negative direction here, the function values are also getting large in the negative direction. And the same thing happens for the fifth power. I won't draw the arrows, but you can see as x gets big here, the function values are getting very, very big. And as x goes to negative infinity, the function values are also going to negative infinity. So that is what we mean by end behavior. So basically, on one side, the function is going up, and on the other side, the function is going down. Now, when you have an even power, the domain is still all real numbers, but the range is only from 0 to infinity. And the end behavior is also a little bit different. And to help us understand that, I brought in the graphs of x to the second power, x to the fourth power, and x to the sixth power. And you can see the domain is all real numbers for all of these. But you can also see that you do not get any negative y values. There is no graph down here for any of these. So that is why the domain is all real numbers, but the range starts at y equals 0 and goes to infinity. Now the end behavior is also a little bit different. And I'll just summarize this on one of the graphs because they all behave the same. But notice that as x gets big, as x goes to infinity, the function values here are also going to infinity. And in the other direction, as x goes to negative infinity, notice that the function values are still going to positive infinity, right? So in other words, it doesn't matter if x is getting big in the positive direction or if x is getting big in the negative direction, the function values get big only in the positive direction. Now, why does that happen? It's very simple. When you plug in a large negative number and you square it, the squaring makes it positive, right? And that also happens when you raise it to a fourth power or a sixth power. Because if you just take a number like negative 100, when you square it, you get positive 10,000. If you take a number like negative 100 and you raise it to the fourth power, you are going to get a very large number, 100 million, in fact, okay? So when you square or raise to the fourth power or raised to the 6th power, or any even power for that matter, a very large negative number, you get a very large positive number. So we say that the end behavior there is as x goes to infinity, x to the n also goes to infinity, and as x goes to negative infinity, x to the n also goes to negative infinity. So a way to summarize this in more simple terms is when you have an even power, the graph goes up on both sides, right? Instead of when you have an odd power, it goes up on one side and down on the other side. That's what we mean by end behavior. Now, when we look at more complicated polynomial functions, you're going to see that lots of things can happen in the middle, but in terms of end behavior, it always behaves in this way. Now we'll look at the graphs of a couple of very simple transformations of x to the n power. So for the first graph, we would like to graph g of x equals x minus 1 to the 4th power. So we need to keep in mind, what does x to the 4th power look like? Well, we had it on the preceding page, and x to the 4th power, for the most part, is a graph that looks like this. So it looks kind of like a parabola, even though it is not a parabola. So when we have x minus 1 to the 4th power, that's just going to move this graph to the right 1 unit. So instead of the bottom of this graph happening at 0, 0, what's going to happen is the bottom of this graph is going to happen at 1, 0. And from there, it's looking like this. And again, this is not a perfect graph. This is just a basic description of what is happening there. And for the second one, the transformation of g of x equals negative x cubed plus 1, we first need to have an understanding of what does x to the 3rd power look like. And from our previous page, you should remember that x to the 3rd looks something like this. So when we graph negative x to the 3rd, the negative is just going to take this graph here and turn it upside down. So everywhere it's below the x-axis, it will now be above. And anywhere it's above, it will now be below. So that graph would look like this. And so this is the graph of negative x cubed. But then we also have plus 1. And the plus 1 is going to take this point here and every other point on the graph, and it's going to move it up 1 unit. So the final graph looks like this. And so we can get basic transformations of the power function by just shifting graph left to right or doing reflections and the other various things we learned in previous sections. All right, so now we're going to talk a little bit more about end behavior. In addition to the power of the polynomial telling you about end behavior in terms of whether that power is even or odd, the leading coefficient also tells you about that end behavior. So we have a summary down below here. Here it says an is positive, so that means the leading coefficient is positive, and n, which is the power, is odd. And we know already that when you have a positive leading coefficient and the power is odd, we know that it goes up on the right side of the graph and it goes down on the left side of the graph. Now in the middle here, lots of different things can happen, but this is the end behavior of the graph. In the second graph, if the leading coefficient is positive, but the power is even, we know that it goes up on both sides of the graph. In the last two graphs, we look at what does the graph look like if the leading coefficient is negative and the power is odd versus the power is even. Well, if the leading coefficient is negative, basically instead of going up on the right side and down on the left side, it's now going to go up on the left side and down on the right side. And in the case where the power is even and the leading coefficient is negative, instead of going up on both sides, it's now going to go down on both sides. Now, if you're completely lost at this point, you're not you just don't know what I'm talking about with this end behavior, don't worry. We'll be doing lots of graphs, and we'll talk about that end behavior in each graph. So here we have an example where it says to determine the end behavior of the following functions by examining the leading term. That's not exactly accurate. We need to look at the leading term and the degree. So in this first example, f of x is 1x to the third. So our leading coefficient, which is called a3, because it's a third degree polynomial, is equal to 1. And 1 is positive. So we have a positive leading coefficient, and the degree n is 3. And 3, of course, is odd. So when your coefficient is positive, your leading coefficient is positive, and your power is odd, the end behavior is that it's going to go up on the right side and down on the left side. Now, the way we can say that is we can say as x goes to positive infinity, the function is also going to go to positive infinity. So that describes what's happening on this side. And then for the other side, we'll say as x goes to negative infinity, the function f of x is also going to negative infinity. So as x goes in the negative direction, y also goes in the negative direction. For the second example, we have a leading coefficient of -2, and technically that would be a4 because it is the coefficient of the fourth degree term. The power of the polynomial here is 4, which of course is even. So what does the graph look like when your leading coefficient is negative and the power is even? Well, we know that if the power is even and you have a positive leading coefficient, then the graph would have gone up on both sides. But because your coefficient is negative, the end behavior is that it's going to go down on both sides. So what that means is as x goes to infinity, f of x will be going to negative infinity, and as x goes to negative infinity, f of x will also be going to negative infinity. So as x gets large in the positive direction, y gets large in the negative direction, and as x gets large in the negative direction, y is also getting large in the negative direction. So this is how we can describe that end behavior algebraically, right? And this is how we can describe that end behavior graphically. Next, we shift our focus to finding real zeros and x-intercepts. So in the previous section, we talked about how zeros and x-intercepts are essentially the same thing. So if you're asked to find the real zeros of a function, we know that the way to do this is to let f of x be equal to 0. So basically, you take what your function is equal to, which in this case is 2x cubed minus 18x, and you set that equal to 0. And then we just need to solve that equation. We can solve this by factoring. We can factor out a greatest common factor of 2x. And if you pull that out, you get x squared minus 9 left over. And then you can keep on factoring. X squared minus 9 is the difference of two squares. And we can factor that down to x minus 3 times x plus 3. So now when it comes to finding zeros, we're going to take every factor that has the variable x in it, and we're going to set each of those factors equal to 0. So for this first one, if we divide by 2, we get x equals 0. For the second equation, if we add 3, we get x equals 3. And for the third equation, subtracting 3 gives us x equals -3. So the real zeros are going to be 0, 3, and -3. And if I want to write those down as x-intercepts, I'm going to write that down as 0, 0, 3, 0, and -3, 0. So for x-intercepts, you basically just take your real zeros, 0, 3, and -3, those become your x coordinates, and for x-intercepts, the y-coordinates are always 0. And what this means is that if you were to graph this polynomial, which I am not going to do completely here, but if you did, we know that it would have an x-intercept at the point 0, 0, the point 3, 0, and the point negative 3, 0. And when you combine that with the end behavior, we can sketch a graph relatively quickly. Okay, so we'll be talking about that in the coming examples. So when it comes to hand sketching the graph of a polynomial function, there are some steps you want to go through. So you want to think about the end behavior of the function. You want to go ahead and find the y-intercept, which is a pretty easy point to find. You also want to find and plot the x-intercepts of the graph. And then you need to figure out whether the graph is above or below the x-axis for each of these smaller intervals. And then you use these plotted points and the end behavior to sketch a smooth graph of the function. And if you need additional points, you can always plot a few additional points if you need it. So let's take a look at an example. We want to sketch the polynomial function here, which is f of x equals x cubed minus x. So first of all, let's think about the end behavior. We know we have a leading coefficient of 1, so we have a positive leading coefficient. And the degree of our polynomial is 3, which is odd. And so we know in this case it's going to go up on the right side and down on the left side. That is the end behavior of this polynomial. So we'll keep that in mind. Next, let's go ahead and find the y-intercept. Now, if you've forgotten, to find the y-intercept, you simply let x be equal to 0. So when I plug 0 in for x, we get 0 cubed minus 0, which is 0. So the y-intercept is 0, 0. To find the x-intercepts, we're going to let f of x be equal to 0. Now, I know this might sound the same, but here we plug in the number 0 for x to find the y-intercept. But for the x-intercept, we let f of x be equal to 0. So we substitute 0 in for f of x. And that gives us x cubed minus x equals 0. We can solve that by first factoring out an x. And then we can factor x squared minus 1 as the difference of two squares. And then when you set each one of those factors equal to 0, we will get x equals 0, x equals 1, and x equals negative 1. And so the x-intercepts are 0, 0, 1, 0, and negative 1, 0. And yes, I will point out that the point 0, 0 is both an x-intercept and a y-intercept. Okay, now let's go ahead and see on a graph, what do we have so far? So now for the graph, we had the y-intercept was the point 0, 0. And the three x-intercepts were once again 0, 0, 1, 0, and negative 1, 0. And we know that the end behavior is that it goes up on the right side and down on the left side. But to get a more accurate picture, we need to see what happens in between these values. So for that, I can just pick a value of x between 0 and 1. I think x equals 1/2 is a good candidate. And then f of 1/2, we just plug the number 1/2 into the function. So we get 1/2 cubed minus 1/2. And this is 1/8 minus 1/2, which is negative 3/8. So at 1/2, at x equals 1/2, y is negative 3/8. So that is right about there. And then if I plug in x equals negative 1/2, f of negative 1/2 is negative 1/2 cubed minus negative 1/2, which is negative 1/8 plus 1/2, or 3/8. So when x equals negative 1/2, we get y equals positive 3/8. So now we're starting to see a little more detail about how this function behaves. We can see that it's going something like this in between negative 1 and positive 1. And the nice thing is we know the end behavior. So we know this function is going to take off in this direction on the right side, and we know it's going to take off in this direction on the left side. Now, if you still are not totally confident about how the function behaves, you could always plug in an additional point. Now, I don't think this is necessary here, but let's just plug it in anyway. If I plug in x equals 2, f of 2 would be 2 cubed minus 2, which is 8 minus 2, which is 6. So that gives us the point 2, 6, which is right here. And if x is equal to negative 2, f of negative 2 is negative 2 cubed minus negative 2, which is negative 8 plus 2, or negative 6. So negative 2, negative 6 is this point. So now we have a really good idea about how this graph behaves. So we're coming up like this. It's going to come through the x-axis here, roundabout like this, and then take off in the other direction. And so if I just go ahead and plot the sketch of this graph, this is what it's going to look like. And this is a reasonably good graph of the function. We have all the important details in there. Next, let's talk about multiplicities of real zeros and what that means in terms of the behavior at the x-intercept. So here I have an example of a factored polynomial function. And you can see that one of the factors, x plus 3, is raised to an even power, and the other factor, x minus 5, is raised to an odd power. These powers are called the multiplicity. So we say that x plus 3 has a multiplicity of 2, and x minus 5 has a multiplicity of 3. The multiplicity determines the behavior at the x-intercept, and it works like this. If it has an odd multiplicity, then the graph is going to go through the x-axis at that point. But if it has an even multiplicity, the graph is going to simply touch the x-axis there, but it is not going to pass through the x-axis. So the multiplicity of the factors, or sometimes they will say the multiplicity of the zeros, tells you about the behavior at the x-intercept. Let's take a look at an example. So in this example, we are asked to determine the multiplicities of the real zeros of the following functions, and then determine whether the graph crosses the x-axis or just touches it at the x-intercepts. So for the first function here, you see we have x minus 6 to the third power. So the 0 for the factor x minus 6 is x equals 6. And its multiplicity is equal to 3. So because it has an odd multiplicity, we know the graph is going to go through the x-axis at x equals 6. The other 0 comes from the factor x plus 2, and that 0, of course, will be x equals negative 2. Its multiplicity is 2 because it is raised to the second power, and so it has even multiplicity. So what that means is at the 0 x equals negative 2, the graph is going to touch the x-axis at that value, but it will not pass through. For the other function, we can't tell the zeros or the multiplicities until we do some factoring. So if we factor this, we get h of t is equal to t times t squared plus 2t plus 1. And then if we factor the remaining part, we have t plus 1 times t plus 1. And so this is t times t plus 1 squared. And I will point out that t is raised to the first power. So let's talk about the zeros and their multiplicity here. So the first 0 is the number that makes this factor 0. And of course, that is the number t equals 0. And its multiplicity is equal to 1. So its multiplicity is odd. And if the multiplicity is odd, it will pass through the axis. And in this case, it's the t-axis. So it will pass through the t-axis at t equals 0. The other 0 for this polynomial is t equals -1, which comes from this factor. And that multiplicity is equal to 2, which is even. And again, anytime you have an even multiplicity, that means the graph will touch the t-axis at that point, at t equals -1. And so just for fun, I brought in the graphs just to corroborate what we just talked about. So we said that at x equals 6, it should go through the x-axis. So here's the graph of that function. You can see it here. And you can see, indeed, at x equals 6, the graph goes through the x-axis there. At the other 0, which was x equals -2, which is this 0 right here, we can see that we said that it was supposed to just touch the x-axis there, and that is what happened. It came up and touched the x-axis, but it did not pass through it. So we were correct on that one. And for the second graph, we have a 0 of t equals 0, and we said that it's supposed to go through the t-axis at t equals 0, and you can see that that indeed does happen right here. That's where t equals 0, and the graph is going through the axis there. At the other 0, which is t equals -1, that's this point right here, you can see that we said it should touch there but not go through it, and that is exactly what happened, right? The graph comes up, touches at that point, but then goes back down. So it touches here and it goes through here. So the multiplicity of the zeros or the multiplicity of the factors will tell you about the behavior at the x-intercepts. Another thing we can do when graphing polynomials is we can check for symmetry. So for this, we're talking about whether the function is odd or even. So let's remember that a function f of x is even if f of -x is the same as f of x, and a function f of x is odd if negative f of -x is equal to f of x. Or another way we can say that is if f of -x is equal to negative f of x. So let's go ahead and run the test for this particular function. We have f of x is x to the 4th power plus x to the 2nd power plus x. To determine whether it's even or odd or neither, we need to figure out what is f of -x. So if we plug in -x, we get -x quantity to the 4th plus -x quantity squared plus -x. And raising a negative to an even power cancels the negative. So we get x to the 4th plus here we get x squared. But on the end, we have plus -x, and that's to the 1st power. So that's just going to end up being -x. Now, I want you to notice that f of -x is this, but this is not equal to f of x, right? Because f of x was this function. And in f of x, you have a positive in front of all 3 of the x terms. And we have a negative here. So this is not the same as f of x. So what that means is that the function is not even. But then I also want you to notice that if you take the opposite of f of -x, that will just be the opposite of what we ended up with. And that would be negative x to the 4th minus x squared plus x. And you should notice that this is also not equal to f of x. And that means that it is not odd. So this function turns out to be neither even nor odd. Now, what's the big deal about even and odd? Well, remember that if a function is even, it has symmetry across the x-axis, so it might look something like this, for example. This is an example of a function that would be even. And if the function is odd, it will have symmetry through the origin, so it could be a function that looks like this. So if you know that a function is even or odd, it can tell you a little bit about the graph of that function, which could make it a little bit easier to graph. So in our next example, we want to sketch a complete graph for the following function. We have f of x is equal to negative 2x to the fourth plus 8x squared. So we're going to bring in all of the elements that we talked about. Now, when I do this, I like to kind of go in order. The first thing I want to do is find the x-intercepts. And to get the x-intercepts, we just take the function and set it equal to 0. And we can typically solve this by factoring. So I can pull out a negative 2x squared, and that will leave us with x squared minus 4. And then if we keep on factoring, we will end up with negative 2x squared times x minus 2 times x plus 2. And the solutions here to this equation are x equals 0, 2, and negative 2. And so these will be our x-intercepts. To find the y-intercept, we simply let x equal 0. So we do f of 0, which in this case is negative 2 times 0 to the fourth plus 8 times 0 squared, which is 0. And so our y-intercept is 0. So if you're talking about intercepts, remember we should usually be talking about points. So our x-intercepts are 0, 0, 2, 0, and negative 2, 0. And now we just found out that our y-intercept is also 0, 0. So we have our x and our y-intercepts. We can go ahead and bring in a graph to start sketching it. So we have x-intercepts at negative 2, 0, and positive 2. And so what we need to do next, oh, and by the way, the y-intercept is here, right? We already have that graphed. So what we need to do next is find out how does the function behave in between. So let's plug in, say, x equals 1. That's in between 0 and 2. And let's also plug in x equals negative 1. And when we plug those in, we get f of 1 is equal to negative 2 times 1 to the fourth power plus 8 times 1 to the second power. And if we do the math on that, that is negative 2 plus 8, which is positive 6. And if we do f of negative 1, we get negative 2 times negative 1 to the fourth power plus 8 times negative 1 to the second power. And this is also negative 2 plus 8, which is 6. And so we can see at positive 1, we have a y value of 6. And at negative 1, we have a y value of 6. And so this is kind of interesting. This function seems to be behaving rather strangely. So let's talk about multiplicity. You can see that the x-intercept 0 has a multiplicity of 2. So what that means is that the graph simply touches at x equals 0, but the other two x-intercepts, positive 2 and negative 2, those have multiplicity of 1, right? Because the powers here are 1, and that means it goes through the x-axis at those values, at x equals positive or negative 2. So at these x-intercepts, it's passing through, but at this x-intercept, it is simply touching. The last thing to talk about is the end behavior here. We have a negative leading coefficient, and we have an even degree polynomial. So we know that the end behavior of a function like that is that it should go down on both sides. So once we establish all of this information, we can sketch a graph of this function like so. And please understand that this is not a precise graph, but it has all of the important elements, the important behaviors of this graph. So here's an example. Here we want to find a polynomial f of x of degree 4 that has zeros at -1 and +3, and each of those zeros have a multiplicity of 1. And it also has a 0 at -2 with a multiplicity of 2. So let's organize our information here. We have 3 different zeros. We have a 0 at -1, we have a 0 at +3, and we have a 0 at -2. And those each have a multiplicity. X equals -1 has a multiplicity of 1. X equals 3 has a multiplicity of 1, and x equals -2 has a multiplicity of 2. And so we're just getting that information from what they told us. Now what that means in terms of your polynomial is that your polynomial will be made of factors that are determined by those zeros and their corresponding multiplicity. So for x equals -1 to be a 0, that means that x plus 1 would be the factor, and it will be raised to the first power because the multiplicity is 1. If x equals 3 is a 0, then x minus 3 will be the factor, and the multiplicity there will also be 1, so it's raised to the first power. And if x equals -2 is a 0, then x plus 2 is the factor, and its multiplicity, they tell us, is 2. Now, if you're wondering how I get the factors from the zeros, it's really pretty simple. When you have a factor, just for example, when you have a factor like x minus 5, if you set that equal to 0, you get x equals 5, right? So whatever the 0 is, the factor is going to be x and then the opposite sign of that number, right? So x equals 3 is the 0, x minus 3 is the factor. X equals -1 is the 0, x plus 1 is the factor. So I just wanted to explain that little aspect there. Now we can get the polynomial function itself, f of x, by simply multiplying all of these factors together. So that's x plus 1 times x minus 3 times x plus 2 to the second power. Now, all I have to do to finish this is just multiply it out. So if we multiply out these first two factors, x plus 1 times x minus 3, we get x squared minus 2x minus 3. I will also multiply out x plus 2 to the second power. So remember, just think of that as x plus 2 times x plus 2. And when you do that multiplication, you get x to the 4th plus 4x plus 4. Oops, sorry, x squared, not x to the 4th. I'm getting ahead of myself. And now to get the final polynomial, we are going to multiply these together, and that means we have to take every term here and multiply it to every term over there. And so when you do all this, you get lots and lots of little products there. So we'll go through, we get x to the 4th plus 4x cubed plus 4x squared. That's when you multiply x squared to all of these. Then we get -2x cubed, -8x squared, and -8x, and that comes from multiplying -2x to all of these. And finally, we get -3x squared, -12x, and -12. And that comes from multiplying -3 to all of these. And when you combine like terms here, you end up with x to the fourth plus 2x cubed. So that comes from these two. And then we're going to have minus 7x squared. That comes from combining those terms together. And then we have negative 20x. And finally, minus 12. And so notice, in the end, what do you have? You have a polynomial function. The degree is 4. And we know that it has zeros as given in the beginning because we created this polynomial by multiplying those factors together. In our last example, we look at decorative gift boxes. So here it says we're going to make a box by taking a 10-inch square piece of cardboard, and we're going to cut out little squares on each of the corners. And then we will fold up the sides to make a box. So this blue square you see here, that's the bottom of the box when it has been formed. So we want to talk about what is the volume of the resulting box. So let me give you a little bit of a crash course in rectangular prisms. If you have a box that has a length and a width and a height, we know that the volume of that box is the length multiplied by the width multiplied by the height. So what we need to do in this particular case is we need to determine what is the length, what is the width, and what is the height. This blue square here is the bottom of the box. Now I want you to notice that the length of this side is 10 inches. The length of this little segment is x, and the length of this little segment is x. So the length of this portion right here is 10 take away 2x, right? We're just taking the whole length here and subtracting off the parts that we're folding up. We can also find the length of this side by doing the same thing. We have a total length of 10 inches, and if we subtract x here and subtract x here, the length of this side is also 10 minus 2x. So the length of this box is 10 minus 2x. The width of this box is 10 minus 2x. Now we just need the height of the box. Well, the height is x because these sides right here, these get cut out and we fold those up, and that becomes the height of the box. So the height is x. Once we know that, we can get the volume of the box by simply multiplying those together. So volume is equal to, when you multiply length, width, and height, it doesn't matter the order that you multiply. So I'm going to multiply x times 10 minus 2x times 10 minus 2x. And this is x times, I'm going to do this multiplication first, which is 100 minus 20x plus 4x squared. Combining like terms, we get 100 minus 40x plus 4x squared. And finally, distributing the x, we get 100x minus 40x squared plus 4x cubed. And then I'll write that volume function as a polynomial in descending order. So we have 4x cubed minus 40x squared plus 100x. So that is our volume function. Next, they want us to graph the volume function and then use the graph to determine the values of x for which the expression makes realistic sense. So to graph this, let's first talk about our zeros. Our zeros are going to be x equals 0 and x equals 5. And that comes from simply taking these factors and setting them equal to 0. So I'll show my work here. If I set 10 minus 2x equal to 0, we get 10 is equal to 2x. And then dividing by 2, we get 5. Now, I will point out that x equals 5 has multiplicity equal to 2, whereas x equals 0 has multiplicity equal to 1. So do we all understand why the multiplicity is 2 here? Yeah, it's because 10 minus 2x, you can see you have two factors of 10 minus 2x, right? So you could have written this in the beginning as x times 10 minus 2x to the second power, okay? So we can see multiplicity here is 1 and multiplicity here is 2. Now what that means in terms of the graph, let's go ahead and bring in a graph, is that we will have an x-intercept at 0 and another x-intercept at 5. And don't pay any attention to the y values here on this graph. We know that the graph is just going to touch at x equals 5 and it will pass through at x equals 0. And we also know that the end behavior tells us that we should be going down on the left side and up on the right side. So what does this graph look like? Well, it goes something like this. Now again, please don't pay attention to these y values because those are not correct, okay? But that's what the graph looks like. Now it asks us to determine the values of x for which the expression makes sense. Remember, x in this problem is the piece that they are cutting out. So you're cutting out x inches on the corner here, on all of the corners. So we know that the amount that you cut out can't be negative. So we know that x can't be negative. So this part of the graph doesn't make any sense. But we also know that the amount that you cut out can't be more than 5, right? Think about that. Because if you cut out 5 inches on this side and 5 inches on this side, you have nothing left because it was only 10 inches across to begin with. So it doesn't make any sense to cut out more than 5 inches. So the only piece of the graph that makes any sense is this piece of the graph right here.